We all know that every coding question ends with a follow-up question of what is the time complexity of this algorithm. Yet, we all struggle to answer this very question. In today's video, I am going to show you how to analyze the time complexity of a given algorithm. So without any further ado, let's get into it. Hello everybody, my name is Ram Kumar and welcome to Sprint Master. Time complexity is the term used in computer science to analyze the time taken by an algorithm. In simple words, if you have an algorithm which has got n operations and each operation takes at least 1 unit of time, then the total time complexity of this algorithm is defined as O of n. There are three different ways in which time complexity can be measured. The first one is big O notation, and it is represented with big O. And the second one is omega, which is represented with omega. And the third one is theta. So out of all three, big O notation is the most common and widely used notation across computer science. So we are going to talk about how to analyze the big O notation of the given algorithms today. Before we get into our topic today, I want you to do me a quick favor. Please click that like button so that you can help me get my video reach to more people. Now let's take a look at the simplest and the smallest time complexity, which is O of 1. Consider this example here. This algorithm has got only one operation, which is to print hello world. And assuming this operation takes 1 unit of time, the total time complexity of this algorithm is going to be O of 1. And this is also called as constant time. This is called constant time because of the fact that no matter how many times you run this algorithm, it is going to take the same amount of time. Now you may ask me, what if there is another operation on top of this system.println, something like another system statement, system.out.println hi. So assuming this also takes 1 unit of time, will the time complexity be O of 2? No, it doesn't work like that. As long as your algorithm's time complexity is not influenced by some kind of a variable, then it is represented as a constant time. And in this case, you don't have any variables or number of operations doesn't change for this algorithms no matter how many times you run. So it is always going to be a constant time and it is represented as O of 1 or a constant time. Now you may ask me how a variable can influence my time complexity. I'm going to show that with this following example. If you take a look at this algorithm, the total number of operations in this algorithm is going to be dependent on this variable n. For example, if your n is 1, your loop will have only one iteration and the total number of operations is going to be 1. And if your n is 10, you have total of 10 iterations going on with this for loop and the total number of operations is going to be 10. So the time complexity of this algorithm is directly dependent on this variable n, and hence it is represented as O of n. Now what if there is another for loop on top of that? J is equal to 0, j less than n again, j plus plus, something like this. In this case, for every iteration of this first loop, you are doing n operations on top of that. So the total time complexity of this algorithm is going to be n plus so on plus n, and this is total n times. In other words, it can simply be represented as O of n into n, which is O of n square. Now what if there is another loop on top of this one, and it again comes up as O of n into n into n, which is O of n cube, and so on. Now that we have understand the time complexities of O of n square and O of n, let's try to find the time complexity of this algorithm. So if you see in this algorithm, we know that the time complexity of this piece is going to be O of n square, and the time complexity of this one is going to be O of n. Now you may jump into the conclusion that the total time complexity of this algorithm is going to be O of n square plus n. But this is not the time complexity of this algorithm. It can simply be represented as O of n square. Though it may be true that it is O of n square plus n, in computer science in general, for the time complexity, we take only the dominant term for the time complexity. And in this case, it is n square. So the time complexity of this algorithm is going to be O of n square. So far, we looked at the time complexities of O of 1, O of n, and O of n square. Now let's try to understand the time complexity of O of log n. So logarithmic time complexity can be explained best with binary search algorithm. I don't want to explain this algorithm in complete, but I want to give you a brief idea of how a binary search works. For a binary search, you are passed with the parameters of array, the left index, the right index, and then the search element. So let us say you have an array of size n, and here the left index is represented with L and the right index is represented with R, and this array is already sorted. Now what you do is you try to find the mid element of this array. You do that by using this equation L plus R by 2, and you equate that with some kind of a mid element. Let us say this is mid element. Now what you do is you compare if this particular value in this array is equal to this search term. If it is equal to X, say array of mid is equal to X. If it is equal to X, then your search is done. You return this mid value and you're done with this algorithm. If it is not equal to X, and what if it is greater than X? If your middle element is greater than X, that means that since this array is sorted, your search element can lay somewhere between left index and middle index. So what you do is you recall this binary search with the parameters of left index, middle instead of left and R. Now you are dividing your array into half and you are doing search on this particular piece. Now what if your middle element is less than X? That means that your search element can stay somewhere between middle and R, and for this case you pass the left index and the right index as middle and R. So that is what is happening right here and here. Now that we understand how the binary search works, let's try to deduce the time complexity of this algorithm. So again, starting with your array of size n. So when the array is of size n, you are doing one operation to actually find this particular middle element, and you are doing a comparison on top of that. So for array of size n, you are doing one operation. And then what you are doing, you are splitting this array into two parts, two equal halves, and doing the operation again here. So for n by 2 size, you are doing one operation again, and then you are going to split this again into two halves, which is n by 4 this time. So for n by 4, you are doing one operation. You do that so on until you find the elements, or you are until to the last element of this array. So the last element can be n by n, and for this you are doing one operation again. We are interested in total number of these operations, right? So let us say the total number of operations are k here. So if the total number of operations are k, then n can be represented as n is equal to 2 power k, because you are exactly dividing into half in every iteration. So 2 power k will be the n, and in this case, if you want to calculate the value of k, that will be log n, and hence this is the value we are interested in. The total time complexity of this algorithm is going to be log n. I know this might have confused you a little bit, but one simple trick to identify logarithmic time complexity is like if you have some kind of n elements and if you are dividing it into half in exactly every iteration, then that is going to be most likely logarithmic time. Now that we understand the time complexity of O of log n, let's try to find the time complexity of this algorithm. So in this algorithm, what we are basically trying to do is you are trying to find an element from array 1, an element from array 2, which can add up to a given sum. So let us say your array 1 is something like 4, 5, 6, and your array 2 is something like 3, 7, 6. So, and your sum is going to be, let us say, 12. You want to find an element from this array, an element from this array, which can add up to a given sum 12. Now what you do is you iterate over this array completely using this first for loop. And for each element, you are trying to find an element in the second array which can add up to a given sum 12. That is what this algorithm is going to do. And the time complexity of this algorithm is going to be, since you have a for loop, it is going to be O of n, assuming n is the size of your first array, and then into, for each element in the first array, you are doing a binary search. And just now we learned that the time complexity of the binary search is going to be log n. And in this case, since we don't know what is the size of this array 2, let us say the size of array is m. Now the time complexity of this algorithm is going to be O of n log m. If the size of array 1 and array 2 are equal, this is going to be O of n log n. So far we have discussed the most common time complexities that you may come across your day-to-day life. Let's recap what we have learned. You have learned about time complexity O of 1, O of n, O of n square, O of log n, and O of n log n. Along with these time complexities, there are a couple other time complexities which are worth discussing. O of 2 power n and O of n factorial. So these two time complexities are a little complicated and I don't want to discuss them in today's video. I can do that in a later video, but the most common example for time complexity of O of 2 power n is going to be find all the subsets in a given set. And the most common example for the time complexity of O of n factorial will be finding all permutations of a string. Now if I want to represent all of these time complexities in a graph, the graph will look something like this. So this is going to be O of 1, and somewhere here it is going to be O of log n, and here it is O of n, and O of n square might come up something like this, and O of 2 power n is going to be something like this, and then O of n factorial is going to be like this. So if you look at this graph, this is going to be the worst time complexity and this is the best time complexity, and this is the order. So O of 1 has got time complexity less than O of log n, which is less than O of n, which is less than O of n square, which is less than O of n log n, which I didn't represent here. So O of log n will stay somewhere right here, and then less than O of n square, which is less than O of 2 power n, and O of n factorial. So the time complexities until this are somewhat reasonable, but these two time complexities grow up very rapidly. So try to avoid any time complexities of O of n factorial and O of 2 power n. If you really want to crack the interview, or in general, if you want to be a good software engineer, it is always a good habit to keep check on your time complexities. And lastly, as I promised, the one of the best resources that I know is good for keeping track of the time complexities for the most common algorithms is bigocheatsheet.com. I'm gonna write it here. bigocheatsheet.com. I'm going to drop a link in the description below as well. This website in general gives you the worst, best, and average time complexities of the most common algorithms. You can check it out. I hope you liked today's video, and if you do, please click that like button and share this video with your friends. And also, don't forget to subscribe to Sprint Master and click on the bell icon next to the subscribe button so that you get notified whenever we upload a new video. As always, thanks for watching this video, and this is Ram signing off.